Finally, we'll look at the axisymmetric plume models. Don't forget this is the most common one to apply, especially if it's not known where the fire load will be located, as this model will result in the largest mass flow rate of smoke and therefore the highest system requirements. When looking at the axisymmetric plume, you have to determine whether it's near or far field. Don't forget that if the clear layer height Z is greater than 5 times the longest dimension of the source fire, then this is often considered to be in the far field, and otherwise we would use a near field model. However, I should point out that this varies depending upon which publication or research paper you're reading. Some advice seems to indicate that the far field model gives more accurate results for the situation where Z is greater than 10 times the longest dimension of the source fire. But the far field model is used for clear layer heights far less than this, and there is little doubt that the equation can probably be safely used to predict mass flow rates for clear layers down to clear layer heights of about 5 times the longest dimension of the fire source. In the Fire Engineering Guide SIPSI Guide E, the advice is to use the far field equation exclusively, whatever the value of Z. Some people feel that the values for mass flow rate by the far field equation for values of Z less than 5 times the longest dimension of the source fire are smaller than would be expected in reality. The best advice is probably to stick with the near field model for values of Z up to 5 times the longest dimension of the source fire, and use the far field model for values of Z above this. Now let's start by looking at the near field model first. Here you can see the near field axisymmetric plume model, where m equals Ce times P times Z raised to the power 1.5. M is the mass flow rate of smoke entering the smoke layer in kilograms per second. Ce is a coefficient of entrainment that varies slightly depending upon the height of rise. P is the perimeter of the source fire, measured in meters, and Z is the clear layer height, again measured in meters. Just returning to P briefly, the perimeter of the fire is assumed to be square or rectangular in virtually all cases. There are a few reasons for this. Firstly, fire loading in buildings is often square or rectangular in nature. Look at the desk or table you're sitting by just now, and look at the seats and furniture around you. Not everything is rectangular, but a lot of items are. Secondly, if the fire is being controlled by sprinklers, then these almost invariably are set out in a rectangular array. And thirdly, if we assume that the fire is square or rectangular, we get the largest value for the perimeter that we can get for any given shape. And the larger the perimeter, the larger the amount of smoke that's going to be produced. And so we're erring on the side of safety by assuming that the fire is either square or rectangular in shape. If we were to assume it were round, then we'd actually get the smallest possible perimeter, and therefore we'd be erring away from the side of safety. Looking at Z again briefly, this is the clear layer height in meters, the height from the floor or the base of the fire to the base of the smoke layer. This is laid down by the designer and is decided upon in step 1 when determining the design objectives. This dimension is as much a dimension of the building as the height of the roof or the width of the doorways, so you must ensure that it is correctly identified. As well as being the clear layer height, it is of course also the height through which the smoke plume must rise before it enters the smoke layer, assuming that is that the fire is in the worst possible location, i.e. on the floor. The equation is empirically derived, and it's been validated for values of total heat release rate between 8 kilowatts and 30 megawatts. That's a huge range and includes virtually all fires that we're likely to be interested in inside buildings. The values of QF, or heat release rate density, that this equation has been validated for lie between 200 kilowatts per square metre and 1800 kilowatts per square metre. Again, this is quite a large range and is probably appropriate for most fires in buildings. Also, this model is valid for heights of rise, that is clear layer heights, of up to about 10 times the maximum dimension of the fire. However, as we discussed earlier, it's possible to use the far field model for clear layer heights of around 5 times the maximum dimension of the source fire. Right, now let's have a look at the coefficient of entrainment that applies to this formula. This coefficient of entrainment has a number of different values it can be given, which predominantly depend upon the height of the clear layer compared to the largest dimension of the fire source. If the height of the clear layer, Z, is more than 3 times greater than the longest dimension of the source fire, then the coefficient that should be used is 0.19. Sometimes you'll see this more accurately depicted as 0.188, but 0.19 is accurate enough for most purposes. If the height of the clear layer is less than 3 times the longest dimension of the source fire, then the value that the coefficient should be given is 0.21. This is because as the clear layer height rises, there is a slight reduction in the entrainment that takes place, and a lower coefficient is appropriate for higher heights of rise. There is also another value for this coefficient of entrainment which we should take into account in certain cases, and this is appropriate where the fire is in a small room that only has a single door leading to it. In such a case, the plume might be subject to fire-induced winds which tend to push the plume over and increase the air entrainment, and in this case the value of CE is set at 0.34. In this case, rooms are considered to be small and therefore appropriate for this value of CE when the maximum room dimension is less than or equal to 5 times the diameter of the design fire size. And it must be said that air is only allowed to enter from one direction. If it comes in from 2 directions, then you're unlikely to get the fire-induced winds. Let's now do some examples looking at the simple plume near-field model.